Okay, hi guys. So in this lecture, we'll be starting off with seeing the second method of calculating the Kp and Kc. So let's get started. So the second method is degree of dissociation method. Okay. So it is ideally applicable for decomposition reactions. Okay. So let's take an example of a decomposition reaction. Suppose we have ammonia getting dissociated into, or rather decomposed as a reversible process, into nitrogen and hydrogen. Okay, and another example can be N2O4 getting dissociated into 2 moles of NO2. Another example can be PCl5 getting dissociated into PCl3 plus Cl2. Okay, so percentage degree of dissociation can be written as alpha into 100, where alpha is nothing but the moles of reactants converted into products divided by total or initial moles of reactants. Moles of reactants converted into products divided by initial moles of reactants. Okay, so in a chemical reaction, or in general in any chemical reaction, we can say that value of alpha would range between 0 and 1. Okay, so let's take an example. So suppose we have A, it is getting converted into B gaseous plus C gaseous. Okay, so in this case, let's suppose that the initial moles of A were M and they were not present in the mixture, and according to the stoichiometric method, we can write that at equilibrium, let's say it is only having m minus x moles, and the remaining x moles are with B and C, and the degree of dissociation method says that the second method which we are talking about is degree of dissociation, which basically says that the concentration of the following compounds or molecules at equilibrium would be C minus alpha C, and alpha C would be of our products would be getting formed. Okay, so it can also be used interchangeably with more number of moles. So this was concentration, and if we have to find or rather express it in the moles at equilibrium, so moles at equilibrium can also be expressed in the same way as m minus m alpha, and m alpha was the moles at equilibrium which B and C were found to have. Okay, let's see another question, or rather an example. Suppose we have 2 moles of Hi getting converted into H2 plus I2. So in this case, again initial moles would be, let's say, A and 0 and 0. So moles at equilibrium can be A minus 2x and X and X formed here. Okay, so in this case we can say that, by the way, this was the first method in which we are concerned about the moles at equilibrium. We can also write it in terms of let's say A minus X, X by 2 and X by 2. Okay, so this is part of the same method, where the stoichiometric method, where we write the moles at equilibrium. And secondly, we can write it in terms of degree of dissociation via second method, degree of dissociation. So we can write the same thing in A1 minus alpha, and A alpha by 2 is the moles at equilibrium which the following compounds or molecules will have, supposing that the alpha is the degree of dissociation of Hi. So let's talk about the Kc in this case. So Kc would be concentration of H2 multiplied with concentration of I2 at equilibrium divided by concentration of Hi at equilibrium squared. So Kc would be nothing but A alpha by 2 multiplied with A alpha by 2 and divided by A1 minus alpha squared. Okay, so this was just the moles. We also have to divide it with volume. So this is the moles. You can divide it by volume as well. So V square would be here. Similarly, V square would be here, both cancelling each other out. So finally, we would be having something like A square alpha square divided by 4 times A square 1 minus alpha square, A square, both cancelling each other out. So finally, the value of Kc would be nothing but alpha square divided by 4 into 1 minus alpha square. So this would be the value of Kc in terms of degree of dissociation. Okay, so in the next lecture we'll be discussing on the degree of dissociation in terms of molar mass or vapor density. So till then, good luck and goodbye.